they combine everything we've done, or most of what we've done up to that point. It's going to be the first time really this year we're going to do that. You guys should probably recognize some words up there: mass, particle, conversions. What about mole? You've heard of a mole? Yeah. I'm not talking about that thing on your left arm. I'm not talking about that little animal that looks like a mouse-ish. I'm talking about the chemical mole. How many of you have heard of the chemical mole? That's a little, that's actually quite a few more than what my other groups had. So have you done some mole conversions to this point? What do you know a mole to be then? Just out of curiosity, because some of you have heard of it. Does anyone happen to recall? Yes? Sort of, yeah. Close enough. What is it measuring? Maybe? Question mark? Yes.
I thought it was like the number of atoms or particles to mass.
Okay, they're related. We'll get to that. All right. Well, here we go. To get there, the word mole does represent a number. Okay? And I just want to see if you guys are comfortable with other words being associated with other numbers. What if I had a dozen of these? You can shout this out. How many would I have? So you guys are used to a word representing a number. Yeah. But what if I had these? Now if I had a dozen of these, what would you have? Oh, it's the same. Yeah. Even though it's a different thing. Yeah. What if I had half a dozen of these? 6. Ooh, you guys are pretty good at doing math in your head. Wait until later. What if I had 2 dozen maps? No, we don't want that. What if I had 2 dozen periodic tables? What if I had a gross of these?
144.
Nice. Who knew the 144? So a different word meaning a different number.
It's a gross.
That's a gross.
12 times 12.
12 times 12. Yep. Why? I wasn't there at the meeting. What if I had a ream of this? You guys heard that word before?
I've heard that word. I just
Can't
remember it.
A ream of paper. 500. 500. Okay? But anyway, once again, a third example of a word representing a number, right? Well, as it turns out, this word mole also represents a number. And it doesn't matter what the particles are. It could be markers, it could be pencils, it could be pieces of paper, it could be mats, although we definitely don't want that many mats. So speaking of, what would you say about the size of that number?
It's pretty big.
It's a very large number. Why? Because it takes up a lot of room to write?
Not because
Well, it does that too, but what else?
it's got a large exponent.
10 to the 23rd power. That is ginormous. Okay? Everybody say hi to Colin.
Hi, Colin. The review pack.
Oh. Grab another one. Left hand side. You'll see it. Okay. It's been said that as an analogy. Yep.
Thank you.
It's been said as an analogy that if Paul here were to start counting 1, 2, 3, 4, from the second he was born until the second he died, counting a different number every second that he was alive, he wouldn't even sniff that. In fact, I'm going to guess that if every person that was in the school were to do that, we added all of those up, we're still not going to get to that number. That's a big number. Okay? We can do the math on that to prove that later if you want. Are you okay with that? But anyway, that's a very, very large number. Now, why do we have to have such a large number in chemistry when we're talking about chemistry type things? What types of things are we considering in chemistry? What's that? What kinds of particles? What are we chemistry concerned about? Such as subatomic particles, or why use the word sub? Let's just go, which means atoms. And atoms make up
Everything.
molecules, okay? All right, and all of these things are very, very tiny pieces, okay? So for example, everybody knows the formula for water.
H2O.
H2O, okay. Now I know water is a molecule, H2O is a molecule, but it is made up of how many atoms? Each molecule, 3 atoms, right? So therefore the atoms must be smaller than the molecules, right? Well, here is really close. Hold on. A smidge over 1 mole of water molecules. And therefore the number of atoms must be 3 times that.
Yeah.
Right? So there's a little over a mole of water molecules here, or 6.022 times 10 to the 23rd water molecules. Okay? It's a very small amount. That means particles must be very, very small. Okay? So, how are we going to count those water molecules? Because we need to keep track of the number of water molecules sometimes in various chemical reactions. This explains some things occasionally. Anyway, moving on. So we do need to keep track of some of the number of molecules that are interacting with each other in chemical processes that we're going to be dealing with later this year. So how are we going to keep track? We have to be able to count these things. Can we just like, well, here, count those out.
I can't.
Why not?
Because that's not
You
how
can't
it
count?
works.
You can't count?
No, I can count, but
What do you mean that's not how it works?
His figures are too big.
I understand. So what's the problem? Just count them out.
you've already said that I couldn't sniff that if I counted a number per
Ah,
second.
they're too small. You can't see them, so we can't just go, right? Can't
There are
do
too
that.
many.
There's too many of them. You don't have time to do that. We don't have time to do that.
No,
Okay?
it's
So how are we going to figure out how many molecules are in there, or how many atoms are in there? We have to come up with a different way. Let's try this. Does anyone have lead as one of their metal samples in either of the labs?
Yes.
Yeah.
Yes.
Okay, just only a few of you. I thought there'd be way more than that. Okay. Well, you remember lead, for those of you that didn't have lead, was a really tiny, tiny little bead-like thing. Does that look familiar?
Yeah.
Maybe you guys saw it, even if you didn't have it, you saw somebody else that had it. Okay? Really, really tiny. You know what? Here, count this, please. You need to know how many are in there. What do you mean you?
You sure can.
You can't count either? Gosh, I've got 2 people in the same class who can't count. No, I want to know the number.
Stop.
Within 1%, I want to know the number.
Guess.
11, 12, 13.
So is this something that you're going to, what is that? That's exactly the same comment someone else made today. Because lead's fairly dense. So how are we going to, I want to know the number. That's how I do it. I pass it off to Lucas. Here, Lucas, you go. So what can we do to count them? Freddie had her hand up first. We'll go Freddie first, and then we'll change her answer. You can try yours. Go ahead.
Measure one of the little beads.
Measure what?
One of, if you're talking of those little lead balls, right? Yeah. Measure one.
Measure what?
Measure
lead ball.
One.
Mass.
The mass.
The mass. Oh.
And then add the mass of all of them and divide by.
Okay.
the number.
Okay.
Probably
Oh. Ah. So you're assuming what?
No, I said you should do 3 trials. You were talking.
Oh, so 3 different. Well,
Measure 3 halves of a couple of different
30, 50, 100, which we can relatively easily count. Let's go 100 because that's going to account for probably all the variability in size. Does that make any sense? Okay. So these are like little isotopes of each other, would you say?
Chemistry.
I don't even know which.
Well, you just took a quiz on it, so you better know. Oh wait, you're right. Moving on. So anyway, let's count out 100 of them, maybe. Find out the mass of 100, and then find the mass of this and divide by that number. Oh my golly, we've got the number of little things. Awesome. Has anyone ever been to a real hardware store before? And I'm not talking Home Depot, Lowe's, or Ace. None of those are real hardware stores. I'm talking like service hardware.
Like
Anybody know what I'm talking
hardware
about?
stores.
Has anyone bought nails or screws there before? Have you? Did you count them? What did you do?
Well, they call them boxes.
Oh, sometimes they kind of act like Home Depot and Lowe's. If you ever seen it, they've got these big bins of the nails.
Yes.
And you don't sit there and count 500 nails. But also in that bin, they have a little thing on there that says, this many pounds of nails cost this much money because you're getting this many nails. Same idea as we're talking about here, right?
Yep.
Saves a lot of time. So we need to find a way to be able to keep track of the number of atoms or molecules, whatever it happens to be, with their mass. So as it turns out, 1 mole, which we already said is equivalent to that number, is also equivalent to the average atomic mass on the periodic table for each of the elements. Now, the average atomic masses, we've been saying are in AMUs, but you know that AMUs also have a mass. If you do a little math, we find out that if we're speaking in terms of grams, then 1 mole of any of those atoms has whatever the average atomic mass is of that atom, and therefore it contains 6.022 times 10 to the 23rd particles. Now, what if we're off by a few thousand particles? To this level of precision, not even close to mattering, does it?
Nope.
Okay, so this is going to be a really good way for us to keep track of the number of atoms are involved, or particles are involved in chemical processes. All right, notice I said that average atomic masses are given in grams per mole. So this is why you guys have those periodic tables. We're going to keep track of the number of particles by measuring masses. We've already talked about a couple analogies where that's a fairly appropriate way to do things. So now it just comes down to the fact that we have 3 things that are equivalent to each other. We've always learned here recently this year that as long as you have 2 things that are equivalent to each other, we can make a conversion factor out of those, right? Mm-hmm. How many, that's that whole bringing everything together. Okay, so how many different conversion factors can we make from those 3 equivalencies? When everybody thinks that they have an answer, please, a correct answer. Matt, go ahead.
3.
That is incorrect. Gavin? 2 is also incorrect. Adrian?
9.
Nope. 6? That is correct.
How many?
6.
Okay, was it a, did you lie or just a guess?
This over this.
Yeah.
This over that.
Yeah.
This over that.
And the other way around.
And the reciprocal of each of those.
Okay.
So 6. Okay? Can you see how powerful this is? We have 6 different things we can do. So here's some examples. Oh gosh. McKenna, I need a number.
Like a big number?
Just give me a number. I'll make it into what I want. What do you got? You do a little bit better. 5.86 mole of By the way, did I tell you that's the abbreviation for mole?
M-O-L.
That's it. That's all we got, people.
Instead of M-O-L-E, it's
I-
just mole.
I understand. I am just telling you, you're going to see that. I don't want you to get your pennies in a bunch when you do see that. That's the abbreviation for mole. Anyway, 5.86 mole of Brennan. I need your favorite element.
I know.
Pick an
mine.
element, Brendan. Who? Chlorine.
Scandium.
All right. So, if you're provided with 5.86 mole of chlorine atoms, what mass of chlorine would be present? So, with that question, which two of these three are we going to be using? Mole, obviously, and the average atomic mass, because we're looking for a mass. Did I give you the number of atoms? No. Did I ask for the number of atoms? No, so we don't need this right now. So anyway, we start with our 5.86. Just like any other conversion that we've ever done this year. Set up a little conversion factor. What goes in the numerator? Well, we said we're going to use mole and average atomic mass, and we're looking for mass. So what goes in the numerator? The average atomic mass of chlorine, which happens to be 35.45 grams, straight off the periodic table, right?
Yeah.
What goes in the denominator? 1 mole chlorine. And so now it's just a little multiplication problem. By the way, without touching your calculators, to one significant figure, what's that answer?
7.
Actually, I think we can get to two significant figures fairly closely. 240. I'm thinking 240. I'm thinking 240. All right, let's take our little handy dandy calculators out, see what we get. I mean, wouldn't that make sense if 1 mole had a mass of 35.45 grams, and we had 5.86 moles, we would have significantly more than that mass. So, what'd you end up getting there, Courtney? 207? It could be right. We're estimating. I thought one significant figure would be best. Now, how many significant figures are allowed in that? Yep, just 3. So 207, you say? 208. Okay, so we have 208 grams of chlorine. Somebody had a hand up. Did I answer the question already?
No.
That's because you weren't paying attention. You were talking to Paul.
So when you divide that, you divide it by the 6.022 Like when you divide the average atomic.
On to example number 2. Annabelle, I'd like a number, please. Have fun with this number.
307.
That's not fun enough.
This one is a good, I'm sorry.
That's then the 21st. That's better.
Maddie, I could use an element.
Chlorine.
Oh, you guys are so lame.
All right. Whoa, time out.
I was gonna say.
Okay, how many mole of fluorine atoms does this represent?
Less than 1.
Okay, so now saying this number or anything close to this number gets to be a pain in the rear end. So let's use something else, like say the mole. Kind of like saying a dozen. If I have 2 dozen something, I have 12. Sorry about that. 24. Okay? Well, instead of saying blah, 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 atoms, we can say a smaller number in moles. Okay? So, which two of the three am I going to need this time, Judy? Going to need the moles and the number of particles. Now, I don't think I've told you this yet, so I'm going to do it now. This has, that value has a name. This is just mainly so we can, well, historically it's important, but also so we can communicate with each other without having to say 6.022. It's called Avogadro's number. You may or may not have been introduced to that before.
Avocado's number.
Really good way to remember that.
Amadeus Avogadro was an Italian mathematician back in the 1700s, I believe, that ended up doing some work at some point in time that kind of led towards the development of this value. So they essentially named it after him. Like they do so many things, they name things after old dead guys.
I think somebody way back then.
Well, no, they didn't know about atoms until...
So
He just made a number up.
No.
He wrote it down like
Again,
that said.
did some stuff that led to the development of that. Right. So they named it after. Kind of like they named the unit of force after Newton, and they named the unit for energy after Joule. They named the unit for power after what? What? They named the unit of temperature after Fahrenheit and Celsius, right?
And Kelvin.
And Lord Kelvin. Who's actually, that's not his name, but when he became a knight or whatever, that's what they did. Moving on. So, which two of the three are we going to need here, Rachel? Which two of these three equivalents are we going to need to solve this question? Avogadro's number in moles, right? So, 3.07 times 10 to the 21st atoms of fluorine. What goes in the numerator of my conversion factor? Gosh, who should I pick on here, Joe? Yeah, the numerator. 1 mole.
You put the numerator.
And what goes in the denominator then, obviously? Amber?
The
6.022, Avogadro's number. Please do not touch your calculators.
Someone sounds like they're dying.
I think we can easily get to one significant figure here. What is the result?
2 times.
A lot.
Go ahead, Gavin.
2 times 10 to the negative 2.
I disagree.
Wait, what? I
Fernando?
got it.
0.5
I disagree. Oh, keep going.
times 10 to the
No, it
Negative what? I disagree.
0.5 times 10 to the negative fifth.
I completely disagree.
You're crazy.
How about 0.005? Okay, what's 3 divided by 6? 0.5, but remember it's 10 to the 21st over 10 to the 23rd, so that's 2 more decimal places, right? 0.005? So throw it in your calculator, see what you get.
5 times 10 to the
Negative third.
I messed up.
So Emily, what's for dinner tonight when you go home? I'm sorry, what? Well, because you look like you were deep in thought about what you're going to have for dinner tonight.
I'm going to Chipotle. I'm dressing up as young Chipotle.
Okay, I need a number that you got from correctly entering values into your calculator. That we have.
What do you want?
I just want the answer.
0.5097974095.
5 what? Right, now how many significant figures are valid?
Mine didn't like come up with that.
You didn't get that? I don't think Brody did either.
Mine said air.
Well, that's because you didn't do it right.
No,
I said 5.097 blah 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 and each was
Yeah. Doesn't matter. All right, so how many significant figures are valid here? 3. Currently I have
A lot.
5. So I need to get that to 3. And where do I go from here? I need to round to here. Hey Emily, say hi to Mom for me. If you're gonna throw it that far, you might as well throw it all the way.
Just blatantly watches it fall to the ground.
All right, here we go. Does anyone have any questions on how that came about? Yeah.
Can we write in scientific?
Oh, I don't care. Sure. So 5.10 times 10 to the negative third.
Totally.
Yeah. Who threw the E thing out there? What did you have? Did you have negative? E negative? Then you did it wrong.
okay.
This divided by this. Okay, well this is smaller than that. Okay, I'm just saying, somehow or other you didn't enter the, did you use parentheses?
No.
Good.
Look.
Well, there's your problem.
It wouldn't accept the EE.
No, you're doing it wrong. No, you did, yes it will.
Okay, well if
Yes,
it's
it
saying
will. I know, watch this. 3.07. Right by.
I was gonna wish for you.
No. Got
It
it.
kept saying like quit.
Yeah.
Mine said error the first time, and then I typed the same thing in and I got it. Like, I typed the exact same thing.
No, I can't answer that. Okay. All right, one more. Adrian, you know you're on YouTube now, right? Ready, set, go. There, I already got the answer.
People are gonna be, because that's the thing.
No, I mean seriously, I know, but I'm just saying.
You've been doing this for a while.
Well, I actually happen to know the atomic masses of about half the elements off the top of my head, so that helps.
Simply because you've been doing this for so long.
Right.
Takes mine instead.
But you did well behind on that. It's called silver. Megan, come on, am I gonna have to move you too?
Oh, I see what you did there. I was like, oh, I don't talk that way.
I don't know, are you guys getting around? 2 times 10 to the 24th-ish? No. Won't that do it? So this is like 3, isn't it? And 3 times 6 is 18. What? Well, I'm given grams, I'm asked for atoms. So technically, all I need are particles and the average atomic mass. I arranged it so my grams canceled, and I'm left with atoms.
But why is your average atomic mass in grams? Like,
Because that's how it's written.
but on the periodic table, we're talking, it wouldn't be
Grams.
107.87 grams because one atom of something isn't going to be 107.87 grams.
This is per mole. If you want to be really technical, it's atoms per mole and grams per mole.
That makes sense.
My moles cancel. Yes.
Alright, so if it's on top, you multiply it on bottom, you divide.
Yes. Doesn't matter. You can either multiply and then divide, or you can divide and then multiply. It doesn't matter.
Doesn't matter. The glory of I don't know, science.
Hey, listen. There's probably, I'm going to guess, 6 to 8 of you that get this. There's probably another 6 to 8 that are about here, and another 6 to 8 that you need a little more practice. That's okay. That's normal.
I know there's that one guy who's just like, I have no clue.